So let's look at another example. Let's say we have a barrel and it's half full of a liquid, let's say water. We've got a z-axis up here, we have our x-axis along here, and the distance there is just the radius r. Now let's imagine the water's just sitting in a flat equilibrium position. So if we stare in from this angle here, so if we just look in from this angle, then all we'll see is a flat surface. And I've got that flat surface drawn out here, so that's our x-axis, which is along here. That's our z-axis up here, and that's just the surface of the water we're looking in there. And that's some function of x, so we just get z as a function of x. So the idea is that if we were to rotate this barrel, then we know that the water would be forced from the centre out to the edges, and it would accumulate on the edges. So we would get a curve occurring along this surface. So if we were to look at it from this angle here, what would happen is that it would rise at this surface and then it would drop down below, so the water would rush out through the centre to the edge and it would come back up here. And our question is, what is the shape of this surface whenever the barrel has been rotated? So we'll look at this in terms of the components of the forces. So we can say that if you take any point of the water, now it could be on the surface or anywhere throughout the volume, but we'll just say initially, let's say it's sitting on the surface. We could say that the force due to gravity down this way is going to be the mass of the water times the magnitude of the gravity. So it's just mass times gravity. Now whenever this is spinning, there's going to be a centrifugal force as well, which forces the water out in this direction. So that centrifugal force is Fc, and it's going to be the mass times the centrifugal acceleration, so MAC. But we know we can write the centrifugal acceleration as the velocity squared upon r, and we can say that if we define the velocity as r omega, then we can say that the value here for the centrifugal force is going to be our value of m times the r squared omega squared upon the r. Okay, so just simply put this r omega in for the v squared there. So cancelling out the r's, you end up getting the mr omega squared. So now let's look at the total potential energy V of this little system here. We're going to have the potential energy that acting down the way, so that's just going to be our mass times our gravity times our height. So our height there is the height z. Now the potential energy due to the centrifugal action, well, it's going to be the summing up all of the force times the distances. So it's going to be the force was the centrifugal force, which is going to be our mr omega squared, and we've got to integrate that from 0 to r by dr. Now you'll notice as well that if we were actually sitting in the centre here, then at the centre the potential energy is a maximum at the centre, and the potential energy out of the edges is a minimum. So you can see that there. If we were to actually move into the centre here, then we would be thrown out in this direction. Okay, so the potential energy actually increases as we go in this way. Okay, so it's actually the negative of what we have in this axis. So this is the increase of this axis, but it's actually moving in this direction. So we've got a negative sign in there for the potential energy. So finally we can say that the total potential energy is going to be like mgz times integral from 0 to r of mr omega squared dr. That's a minus sign. So let's go ahead and we'll finish this off in the next slide. So we'll go ahead and we'll integrate the equation from the last slide. So we're just integrating this with respect to r. So the m and omega squared are constants, that becomes r squared upon 2, and we've got our minus sign, and that's from 0 to r. So that's going to give us a value of minus a half mr omega squared. So the total potential energy is going to be mgz minus a half mr squared omega squared. But remember, when we've started rotating this bucket at a constant angular velocity, then we'll have a new shape for the surface of the water, and indeed for all of the water down below as well. And that new shape will be in an equilibrium position. So it means that if you were to pick one particular point, then there won't be any more forces acting on that shape, on that point, and all of the forces will be in equilibrium. So that's really saying, in terms of calculus of variations, that when the potential energy is stationary, the system is in equilibrium, and when it's a minimum, the equilibrium is going to be stable. So it means that we can therefore say that if there's no more forces acting on this point and the forces are in equilibrium, we can say then that the mgz will actually equal a half m r squared omega squared. So we write that out here, and all we need to do now is solve for z as a function of r. So we just take the mg down to the other side to give us 1 upon mg mr squared omega squared. So finally, z as a function of r is going to be half r squared omega squared upon g. So that's the equation we've got here. And we can see here then that the z is a function of r, it's a function of the square of r. So this is a parabolic function. Okay, so it means that the new shape for our water, which is rotating, is going to be a parabola. So that's all there is for this video. I'll get you on the next video. Goodbye.